Should I start? Okay. All right. Okay, let's continue. I should have moved the boards in the break, shouldn't I? Okay. So now you might ask, what do I mean by subregions directly in the continuum? So without going through this thing of having a regulator. And it's actually a subtle question, and we're not going to fully answer it today. So tomorrow we'll talk more about this problem. But for now, let's imagine, we have some continuum quantum field theory, and we think about the Hilbert space as somehow living on some initial time slice, some t is equal to 0 time slice, sigma, and there's some Hilbert space associated to sigma. Then we can imagine splitting up that Hilbert space into two regions, A and A complement, again, like we did in the lattice system. Now we have one reason you might do that is because if I have some operator here and some operator here, so O1, O2, then they commute because they're at space-like separation. So because they commute, you might think we can sort of assign independent degrees of freedom to them. Just like in the lattice system, different Hilbert spaces will, the operators on the different Hilbert spaces in the lattice commute because they're just independent of each other. And in this case, they commute because they're space-like separated. However, now we have a new thing, which is that I can also take an operator a little bit up, OX, and as long as I don't go beyond some kind of light cone that emanates from the boundary here, then this is still space-like separated from operators on this slice here. So, okay, so, good. So that means that, what do I want to say? Okay, so first, let me say a few things firstly here. So we're splitting sigma into A union A complement, and then we might guess that that implies that there's some Hilbert space. This Hilbert space splits up as some tensor product like this. This is actually wrong, but I won't get to that until later. Let's just assume this is true for now, and then I'll fix it later. But now if we have the situation where there's some operator here a little bit to the future in A, then that's still somehow associated to the Hilbert space HA. And you can see that in various ways. One way is that it does commute with all the operators in A complement. So, if it's going to be anything, it's going to be some operator here. The other way is you can think of this as some Heisenberg operator. So O of X is some Heisenberg operator that you can sort of evolve backwards in time. But, it's not going to... its effect is going to be limited by causality. So in principle, I should be able to write this as some operator, as some complicated combination of operators that live on the t is equal to 0 time slice. And so given this, we should actually associate a Hilbert space or some subregion to some causal region, which is now this diamond. So subregions now associated to causally complete regions. So, and another way to think of this is I don't have to work with some fixed Cauchy slice in relativistic quantum field theory. I can pick my t is equal to 0 slice or my initial time slice to be whatever I like. And so as long as it's space-like, I can pick something like this, where now it goes through the point X. And so with this freedom, I associate these subregions to these causally complete regions, And the way to generate this causally complete region from this A is to define the notion of the domain of dependence of A. And so the domain of dependence of A are all points, or space-time points, that are space-like, in this context, separated from A complement. So everything that is space-like separated from here and here defines this wedge region, D of A. And if I pick a different slice, like this A prime here, then D of A prime is equal to D of A. I get the same domain of dependence. Okay? Okay. Yeah, so let me just preview a little because I made this mystical statement about this tensor factorization. Later, we're going to talk about an algebraic approach to this question, where we don't really talk about Hilbert spaces, but we talk about operators that act on the original Hilbert space. So we think about sort of a set of operators that act on the quantum field theory Hilbert space, but in particular, we're interested in subsets of operators. And we're going to be interested in subalgebras of operators that are associated to these regions. And you can associate subalgebras to these regions. So then you define some algebra of operators associated to D of A, and its complement, and so forth, etc. And when we study these in a little bit more depth, we'll find that one thing that you find is that they don't have to form an algebra of operators which comes from a Hilbert space. So it didn't have to come from a Hilbert space, and so in principle there's no reason to expect that there should be a Hilbert space description of this subregion. Okay. And you know.
Sorry, question?
Yes.
But even on the lattice, if it was a gauge theory, but on the lattice, there also the Hilbert space would not split even there, right? Yeah, but that's a different problem and a much easier problem to deal with. So that's still, yeah. So I think, for example, you can deal with that by going to just a larger Hilbert space. I mean, it's not the best way to deal with it, but it's one way. But yeah, this is a much bigger problem, and it's actually, you know, again, I'm making all these mystical statements, but it's related to the UV divergences that I told you about before. It's related to UV divergences that arise at the boundaries of the regions. Okay, so having said that, we're going to go back and pretend like there is a Hilbert space, and then I can define a density matrix, and we'll proceed with that, and we'll try to construct the density matrix. So path integral construction of rho A. Okay. So again, let's pick a state. We always have to pick a state, but I'm going to pick the vacuum. And the reason I do that is it's very simple to prepare the vacuum with a path integral. Okay. And there's a standard sort of Euclidean path integral which computes the wave function of the vacuum. And there's a picture for it and an equation, and I'll write the picture first. So the picture is like this. So we do a path integral in the lower half plane of Euclidean time. So this is Euclidean time. I've Wick rotated. So this is somehow IT. And we do some path integral from minus infinity to the tau is equal to 0 surface. And if you like, this is where my sigma lives, sigma from over there, where we impose some boundary conditions on the quantum fields. So let's say we're interested in a scalar field theory or something. We impose some boundary conditions, phi 0 of x here. And I claim that this picture computes the overlap. It's a number, computes a number which is the overlap of this
field configuration, phi of x. X is just the spatial direction here, with the ground state wave function. Or at least it computes something proportional to that, up to a constant. And why is this? Well, in equations, this is some path integral weighted by the action from some minus infinity with some boundary conditions at minus infinity that we don't really need to specify, up to some phi of t, it's phi 0. If we did specify the boundary conditions here for momentarily, we'll drop that, then this would just be the overlap between this field configuration phi 0 of x, the time evolution operator in Euclidean time for some time t, where t, this is my field at t. So we start at some very big negative t. This is minus t. And then we do this path integral like this, and then we get this state chi here. And if I take big T very large, then I get some dominant answer that comes from the ground state, and then I get exponentially small corrections from other states, assuming that the theory is gapped. So this becomes something like phi 0 omega chi e to the minus t times the energy of the ground state. This stuff is just a constant, right? It's a constant in the sense that once I vary this field configuration, there's a boundary condition here, I'll get different numbers, but these numbers won't change. So I can just say the answer is proportional to this. Okay, and then I can take the large t limit, so this is plus exponentially small corrections. Take the large t limit, get rid of these, and then I get my answer. Okay.
Sorry.
Yeah. Yeah.
I admit that I've got a bit lost.
Okay. I can go slower.
I mean, I got lost when you wrote the path integral and you argued that it had to be proportional to the scalar product. Or,
This guy?
Yes.
Yeah, so the path integral itself computes transition amplitudes, right? In real time, it would compute, the unitary time evolution, e to the I th. But when I Wick rotate, I get this e to the minus th, right? And then this thing at large t just becomes a projector onto the ground state, because anything with higher energy than the ground state will get exponentially damped. So this is kind of standard trick in quantum field theory for projecting onto the vacuum. And as long as chi is not orthogonal to the vacuum, that would be a problem. But if chi is not orthogonal to the vacuum, I can take the limit t to infinity, and it doesn't really, and then I can just sort of leave my fields free when I do my path integral, and not even specify boundary conditions. So the end picture is that the thing we're interested in, phi 0 omega, is just given by this. The picture that I drew originally, let me just draw it again. Phi 0 of x, and this is from minus infinity in Euclidean time. Okay, so is everyone okay with this? Because if you're not, then it's going to get confusing. Do you want me to, does anyone want me to go over that again? Yeah. Okay, all right, I'm going to not. And it's proportional. Okay. And this proportionality, this constant, I'm just going to deal with it later. I'm going to forget about normalizing my states, and then at the very end, I'll normalize. Okay. Okay, so now
Good. Now we want to compute, we're interested in the density matrix. We're interested in the reduced density matrix, but let's talk about the density matrix to begin with. So the density matrix corresponding to a pure state, of course, is very simple. It's just this. But now let's compute matrix elements of this. So we have some phi 0 here and phi 0 prime over here. And the picture we would draw for this is the same picture here. And that would be phi 0 with a boundary condition phi 0 x here. That's this picture. Let me put this here. But then, and that was the ket. But to compute the bra, we flip this picture and we just put it on top here. Like this. So with a boundary condition which is phi 0 x prime. So these are two different field configurations. They don't have to be the same. And you know, the one way you can understand the flipping is that Hermitian conjugation in Euclidean. Right, this is somehow we're taking the Hermitian conjugate of this. Becomes this reflection positivity or reflection. So tau goes to minus tau, so that you have to flip this. This is a property of the Euclidean path integral. Now, you know, I've drawn these next to each other, but there's no relation between these field configurations. Now what we're going to do is we're going to try to do a partial trace. Okay, so we're somehow going to join these when we do that partial trace, so that's why I've drawn them next to each other. So partial trace, what we do is we take phi 0 and we think of it as a tensor product. Again, this is sort of continuing this fiction that we can think of these as tensor products of some field configuration in A tensored with some field configuration in A complement. Right, and so that's A is here in this picture. Maybe I'll use color at this point. So this is A, and this is A complement for both of these regions. So you know, this is somehow the field configuration in the pink region, and this is the field configuration in the blue region. In particular, you know, what this really means is that we take phi 0 of x, it's a function of x, and we decompose it as some function that lives only in A. So this is 0 in A complement, and some other function which lives in A complement. And this is 0 in A. Good. And then to do the trace, what we're going to do is we're going to set the field configuration phi 0 in the AC region for the two, phi 0 and phi 0 prime, to be equal, and then we're just going to integrate. Okay, and when we do that, effectively what we end up doing is just gluing these path integrals together. Right, so instead of having this boundary condition, so let me write it out, we have phi 0 prime, phi 0 A complement prime here and phi 0 A complement here. We're going to set these equal and integrate. That's what a trace is, right? You set the two things equal and then you sum. And we do that here as well. And what that effectively does is just glues this picture together. And then we're left with this. Glues path integral together. And we're left with a picture that looks like this. Let me draw it in color. We're still left with two different field configurations in the top and the bottom of A because we haven't set those equal to each other. So we still have phi 0 A prime, phi 0 A But out here, we just do a free path integral through this region. And that effectively sums over all of these, setting them equal. Okay? And so what is this equal to? Well, we've done the partial trace over some of the degrees of freedom, and so we're left with the reduced density matrix, but we're left with a reduced density matrix sandwiched between these field configurations. So phi A, rho A, phi A prime. Okay, so this is a picture of this path integral. This should be somewhat intuitively clear just from the picture. You do a path integral on all of Euclidean space, so Euclidean time, all of Euclidean space, we just leave a little cut in the center. And that cut is centered on A, because that's where you're interested in the reduced density matrix. And then to compute the matrix elements, you just feed in particular field configurations on the top and the bottom. Okay? So that's all this is. And this is just a number, right? It computes a number. Yeah.
Why can you split the degrees of freedom between A and A complement in the wave function? I mean, in the field configuration, in that way?
Yeah, it's a good question. you can't really technically. I mean, you can. Let's just pretend like you can. There's significant issues here, and you can already see that. I mean. Do these have to be equal here? Does phi 0a have to be equal to phi 0a prime here? I haven't said anything about that. And if they're not, it seems like right here there's going to be all sorts of issues. So one, yeah, go on.
But is it related to the fact that you can't split the Hilbert space between the two?
Yeah. Okay. Yeah. So one fix for this, and what we'll find is throughout all these calculations, there's some issue. There's always some issue. And you have to deal with it at some point, and that's because you will get sort of infinite answers. But one way to deal with it, this is one way, is to drill a hole here. Just drill a hole. And specify some boundary conditions on the edge of this hole. Okay? So that fixes the problem. It adds all sorts of new things, because you're now specifying new boundary conditions and so forth. Yeah.
But
yeah.
I mean, if the entanglement comes from the small regions where you are splitting your space, how do you know that? I mean, this is kind of a regularization scheme.
That's right.
And how do you know that your result doesn't depend on your regularization scheme?
Yeah, that's a great question. Yeah. Trial and error is sort of the best way that I know how to do it. So that's why it's sort of important. So what I found with doing computations like this, exactly where I do this, is that what happens is if you're calculating something you know to exist in the continuum limit, then whatever you do here, it doesn't matter. So it's already a UV safe thing. So in some sense, it doesn't really matter how you regulate it. And that's what happens when you do the calculation. Yeah, but yeah, these are all very good questions. Yeah. Okay, any other questions? Okay, so this is our basic path integral we're going to do. There's some issue. I'll just ignore this issue right now. Later on, I'll talk more about it. So we'll pretend like we can do that. Now, it turns out that in general, okay, this is true. And the best in general you can do with this is you can calculate powers of the density matrix. So trace rho A to the n, where n is an integer. Okay, and I'll come back to this because this is sort of for more general, for very general regions, maybe some other states that you're interested in. This is sort of what you're left with doing. However, it turns out that for many regions, for some regions and some states, there's a simpler way to do this where you don't have to compute trace rho to the n. In some sense, you can just calculate what this operator is. And you just write out what the operator is. You sort of solve the problem in that way. And so I'll come back to this. This is called the replica trick. And we won't do that now. What we're going to do is we're going to just write down in certain situations what this operator is. Okay, let me... Nope. Okay. So the situations where we know how to calculate this operator, the reduced density matrix, is when there's some symmetries. And so the first case, the classic case, is called Rinzler Space, or involves Rinzler Space. So I'll call it the Rinzler case. And that's where I take A. Instead of taking it to be this interval, like I've been drawing pictures, I'm going to take A to be half of all space. So I take, this is my sigma, my Cauchy slice, or my time t is 0 slice. Again, this is a picture in Euclidean. This is tau and x. I'm going to take my region to be, say this is x is 0. I'll take A to be just x is bigger than 0. Okay, so that's this region here. And just to emphasize, I take my state to be the vacuum. Right? That's implied by this path integral, but just so you know. And so again, we do this path integral where we have boundary conditions above and below. Phi A prime. Now, the way to do this, this path integral, so we're sort of thinking of doing this path integral in Euclidean time, where we slice up the path integral like this. But you can slice up this path integral a different way, in a way where you can just immediately write down the answer. And that way is to use the sort of cylindrical symmetry that's sort of clear from this. So, I pick a new coordinate system, which is, so my original coordinate system is just flat. I'm going to do the 2D case, but this works in general. You just have to add a few more coordinates. But I'm just going to do 2D, so 2D quantum field theory. Then I can rewrite this in cylindrical coordinates, where theta is now the angle around here. So I slice up, I have coordinates that go around like this. And given that coordinate system, it's quite natural to think about doing the path integral in that way. Right? So what that really means is, slicing open the path integral along fixed angle slices. So, in some sense, instead of thinking about sort of time evolution in the time direction, you're thinking about time evolution in the angular direction. Okay? And obviously that's natural for this problem because, then all we're doing is we're doing some path integral in this angular direction by 2 pi, imposing some initial and final boundary condition. Okay? Okay. Now, to fully realize this physics, the physics that's going on here, it's natural to Wick rotate in the new time direction. So this is the new time direction, the angular direction, and I'm just going to Wick rotate. I'm going to send theta to I eta, and then I get a metric which looks like r squared d eta squared plus dr squared. And this is the metric on the Rinzler wedge. So to draw the Rinzler wedge, we go to real time in the usual time coordinates. So I'm going to draw real time here, t and x. And then we draw the causal domain associated to A. Remember, that was in any case what we were thinking the subregion was associated to, this causal domain, d of A. And the Rinzler wedge is just that. This is the Rinzler wedge. Right. And this coordinate system covers the Rinzler wedge. I can draw lines of constant r like this. So these are constant r lines, and these are lines of fixed eta, like this. So this is fixed eta. Sorry. Okay. Okay, and so you go to infinite eta and you go right up to the horizon here. The future horizon, you go to infinite minus eta, you go to the past horizon. Okay, so in the end, what we get is quantum field theory in Rinzler space. And in particular, you ask what is the state associated to the quantum fields in Rinzler space that we should be doing, or that this path integral is giving us. And of course, it's the reduced density matrix for A. Okay, so that's what we're interested in, and that's what it is. So quantum field theory in Rinzler space. And it's governed by rho A, because that's what the path integral was set up to do. Right? And when we Wick rotate, we're getting the physics of that path integral, essentially. But of course, that also makes sense because the Rinzler coordinates only cover this patch, so they don't really know about what's going on over here. So what you do is you take your global state, which is the vacuum on A, and then you trace out on the full Hilbert space, and then you trace out the complement, and you get the reduced density matrix. Okay? Good. Now, because the Euclidean, so if we do, if we do a path integral in, let's say we did a path integral in real time in the eta coordinates, then that would generate, so a path integral gives you transition amplitudes for the time, the time evolution operator, which in this case would be e to the I eta times the Hamiltonian, which generates shifts in eta. So this is the Hamiltonian associated to eta translations. And I write it like this, hc, because xc is some vector, some killing vector, some symmetry of this space, which is associated to this, so it's just d by d eta. It's just this vector. And given that, you can always write down the Hamiltonian associated to this as some integral over the stress tensor over some slice. In this case, we just pick a slice which is A here. So we integrate like this, and that gives us our generator. Okay, and d sigma nu is just the natural volume element perpendicular to this surface, right, which points in that direction. Okay, so then you can just calculate what this is. In particular, it's natural to write xi in flat space coordinates, and it's just this. And then hc is just an integral from dx, 0 to infinity, x t0, 0. So you just get the t0, 0 component. Because we're integrating along A where t is 0, this term vanishes. We just get x d by dt, and this is in the t direction, so that's why we get t0, 0, and then we have this x vector. Okay. Now, why am I telling you about this? This is what a real-time path integral would give you in Rinzler space. Well, what is this path integral? It's a Euclidean path integral. It's a Wick rotation of a real-time path integral where I send eta to I theta, and I do a 2 pi integral. So that means that the density matrix, which is related to this transition amplitude in Euclidean, is just given by just Wick rotating this and sending the parameter or the distance to 2 pi, and that's our answer. Okay. Okay, so at the end of the day, we have an expression for the reduced density matrix that's very precise. It's written in terms of the stress tensor, right? It's determined by this operator, the stress tensor. Okay, and it looks like the Gibbs state, right? But it's the Gibbs state at some funny temperature for some funny Hamiltonian, okay? The Hamiltonian associated to d by d eta, which is then what I should have said is the generator of boosts. Okay, so in Euclidean it's a rotation, but in real time changing eta is moving along different slices like this, and so that's a boost, right? It's a boost that holds fixed this point here. So fixes the boundary A. Okay. Okay, and so what is the physics of this? The physics of this is, again, the vacuum restricted to A looks like this thermal density matrix, but for the generator of boosts. And so if you're some observer that's restricted to A, you'll see a thermal state, and one way to restrict to A is to think about observers that are uniformly accelerating. These are called Rinzler observers. They're the ones that go along these lines, along constant fixed R surfaces like this. And so such observers will see a thermal state. And this is the Unruh effect. And it's sort of reinterpreted as just a statement about entanglement in the density matrix. Okay. And finally, when do I have till? 10 minutes. Just 10, okay. 5 more? After 10 minutes? We'll see, okay. Okay, so the physics, the physics, so let's unpack this formula a little bit more. So we have rho A, let me just write it out, is exponential minus 2 pi integral dx, x times t0, 0, but what is t0, 0? It's the energy density, so I'll call that rho of x. So what this really looks like, if this x wasn't there, this would just be, the Hamiltonian, although just integrated in some region. So what we're getting here is some energy density that is modulated by x. So it's sort of like there's an effective temperature which depends on x. And so, in the usual case, you would have e to the beta h. So then I should interpret 2 pi, 1 over 2 pi x as the effective temperature. All right. And so, given that, we can make a crude estimate for the entanglement entropy of rho A. Because what is the entanglement entropy of this density matrix? It's just the thermal entropy. Okay, so I need to estimate the thermal entropy in Rinzler space, which has this varying temperature. So notice an important fact is that this temperature varies, and it goes to infinity near the boundary of this region. So it becomes you get very hot, very close to the tip here. So observers that are really close are at very high temperature, and these are at lower temperature. So if you imagine, so then the entanglement entropy of rho A should just be the thermal entropy of this state. We can estimate the thermal entropy if, let's say, it's a 2-dimensional CFT. Then the thermal entropy density sort of universally looks like this, at least at high temperatures compared to any other scale. C pi over 3T. That's the entropy density. So to calculate the entropy, thermal entropy, I should integrate this. This is very crude, but it actually gives a very good estimate. So I should integrate from 0 to infinity. This, where I put in for T, the effective temperature. So combining things, you get C over 6. And the temperature goes like 1 over x, so there's a 1 over x. Okay? And so my entanglement entropy is this integral which is divergent in the UV and the IR. Okay? So let's regulate, and then we'll get an answer at least. C over 6. So let me regulate. I'll put a little lambda here, and I'll put an epsilon here. Let me put an L here. Then I get log L over epsilon. Okay. And this is the correct answer, actually. So the IR scale we'll deal with in a little bit, maybe. Might not have time. But it's easy to deal with the IR divergence. The UV divergence you can sort of never get rid of, and it's related to the divergence in entanglement entropy near the boundary of the entangling surface. And it goes like C over 6 minus C over 6 log epsilon. Okay, so we have this. There's some divergence due to entanglement, UV entanglement. Right, so this is entanglement between here and here, right? Very short distance entanglement. And it gives a contribution to SEE, which goes like minus C over 6 log epsilon. Okay. And you can do this much better and more precisely. I'm just giving you a heuristic estimate. You can actually calculate this pretty well. You still have to specify a regulator, but then you can calculate it precisely, and that's what you find. Okay. Okay. Good. There's a similar thing you can do. You can sort of, we've sort of essentially solved the problem because we've written down what the reduced density matrix is. You can similarly solve the problem in another case. Well, there's actually a few other cases I'll list at the end, but let me just go through one more case. For a CFT in 2D, again with a vacuum state, but now reduced to an interval of length L. So it turns out that you can again write down what the path integral, you can again use symmetries to write down this path integral. And the reason for that is that there's actually a conformal killing symmetry, or conformal killing vector, which generates a symmetry that takes you from the top to the bottom. Just like in the Rinzler case, there was this rotation. Now we have some more general conformal rotation that essentially acts like this, close to the regions. And out here it does something like this, and something like this. Okay, so there's again some symmetry that allows you to do this path integral. That symmetry, if we Wick rotate to real time, gives you something that has some flow lines in this d of a. So this is now d of a for this interval. And these, the Wick rotation of these lines, just like we got a boost in the Rinzler case, gives you something that looks like this. And you can write down exactly what this vector field is. It's actually part of the global conformal group in two-dimensional CFTs. And I can look you to references where they write that down, but I'm not going to write it down. At the end of the day, so I'll call it chi. You argue again that rho A is exponential minus 2 pi, the generator associated to this symmetry chi, or this conformal symmetry, Again, you get 2 pi as long as you normalize chi so that it becomes exactly a rotation near the boundary. So it looks exactly like C in the Rinzler case here. And so you get this answer where h chi I can write out as an integral now from 0 to L, T mu nu, chi mu, d sigma nu, which is then an integral dx x L minus x over L T0, 0 from 0 to L. Okay, so this is the factor that you get from doing that calculation, finding out what this vector field is and evaluating it at t is equal to 0. Okay? So this is kind of similar, except you have a slightly different modulating factor. So it's like there's an effective temperature, which is something like 1 over 2 pi times this. So L over 2 pi x L minus x. And again, it's a temperature that diverges as x goes to 0 here or as x goes to L here. Okay? You can take this and you can do the estimate for the entanglement entropy using this idea. Again, it's very crude, but actually gives you the right answer. So yes, except you have a subtlety, there's a subtlety. So the answer that you get, I'll write it here. S, the thermal entropy that you estimate in this way using the entropy density and integrating it, you get, you get C over 3 log L over epsilon. Okay, where L is now really the interval length. Okay, and so notice now you get a factor of a third, so you get the divergence is like minus C over 3 log epsilon, and that should be compared with this minus C over 6 log epsilon, and that's just because in this case you just had one place where you had a sort of infinite amount of entanglement. Here you have 2. You get 2, factor of 2 from that. Okay, and so this is like the answer. This is a well-known formula for entanglement entropy in CFDs in 2 dimensions. Okay, and again, you can do it much more precisely than I'm doing. Okay, so the final thing I want to do with this is, so this is kind of a general. This is a fairly. This is well, it's not very general, but there's a set of cases where you can do this. And it's not just limited to what I've shown you, and it's not just limited to 2 dimensions. So just to give you an incomplete list, these cases also have a name. So this is the cases where the log of the reduced density matrix, which has a name which I'll pull out now, which is called the Modular Hamiltonian. Is local, in the sense that it's an integral over, it's just a local integral over the stress tensor in this case. So it can always be written as some integral over T in the region. There's a sort of a list of cases where this is the case. In general, you can talk about the modular Hamiltonian as the log of the reduced density matrix, and there's absolutely no reason it should be such a simple integral over the stress tensor. Okay. Yes.
Sorry, Tom. So in your example involving the 2D Rinzler case as well as the 2D CFT case, so what goes wrong if you consider higher dimensions?
Oh, nothing, yeah.
Oh, so they should
Well, you have to be more careful. The interval gets replaced by a sphere, or a ball, sorry, a ball.
Yeah. And then you will have to specify, I guess, a boundary condition at the equator, and then...
Yeah, well, then you have divergences at the equator. That's right.
Okay. Yeah. Are there any issues associated with that, like the fact that the divergence is along a continuous line versus like just at 2?
It means you get a different estimate for the divergence. I think, in higher dimensions, these estimates are pretty poor, the ones that I'm giving you. They don't work as well as in 2D. I think somehow just because it's a log, you're getting the right answer. But in higher dimensions, you can still calculate the entanglement entropy using more powerful methods. And yeah, I mean, you have to regulate it in a different way, but it's the same idea.
Okay. Thanks.
So this is going to be on the list if I have time. So yeah, so there's some cases. So if I just have a quantum field theory in d dimensions reduced to the Rinzler wedge, then this is the case. And in the vacuum, if I have again a CFT in d dimensions, and I think about a ball-shaped region, that's my A. The domain of dependence of a ball-shaped region is a double cone. So I draw the intersection of two cones, light cones, emanating from a point, and that gives me this double cone. And again, you can do it for the vacuum. And in 2D, you even have more power. You can do interval where the state is the Gibbs state, as long as the CFT lives on the infinite plane. And then there's all sorts of examples in curve space as well. A classic example is the Hadal-Hawking vacuum of a black hole gives you a local modular Hamiltonian, which is just the energy, which is just an integral of the stress tensor outside of the black hole. So there's a bunch of cases, but it's limited, right? There's a bunch of cases, but it's limited. Okay. All right. So I have 5 more minutes. I want to say one more thing. Okay. So one more thing. So in the case where you have this local modular Hamiltonian, there's one more powerful thing that you can do, which is you can calculate the relative entropy. Okay, this thing that we started with. And so just like, because it's like a Gibbs state, we can do the same analysis that we did for the thermal relative entropy. We wrote it as a free energy. And so in this case, you can also write the relative entropy as a free energy, where it's the change in the entanglement entropy, where change means the difference between rho minus sigma, plus 2 pi, and that 2 pi is just because the temperature is effectively 1 over 2 pi, the change in the expectation value of this Hamiltonian that we've been seeing pop up, HC. And so you can calculate, well, this is kind of hard to calculate. This is easy to calculate, right? It's the expectation value of the stress tensor integrated over some region. There are plenty of states where you can calculate that. And so that it's useful because, well, it's useful for various reasons, but here's one reason that this is useful. So let me just write out what is delta HC. So delta is the difference between the expectation value in these two different states, but this state is the vacuum, remember? So at the end of the day, the expectation value of the stress tensor in the vacuum I can take to be 0 in some of these geometries at least, T0, 0, x. So I get something like this. For example, this is the Rinzler case, Rinzler. But in the other cases, you can write down other formulas. And one nice thing about this is that relative entropy had this property that it was positive. It was always bigger than 0. So let me think about a state, rho, which is somehow a small deformation of sigma, where smallness is controlled by some perturbative parameter lambda. And let me just expand the relative entropy in lambda. Okay, assuming that everything is smooth and nice, I can expand this as a power series in lambda. But lambda is just some parameter. So it has to be the case that the first order term vanishes. And the reason for that is, if it didn't, then it would violate this positivity, because I could flip the sign of lambda. I mean, lambda would be a phase and it wouldn't even make sense. So actually, at first order, in deformations away from the vacuum, you can claim that the relative entropy vanishes. So at order lambda, SREL is equal to 0. That means I can now suddenly calculate the change in entanglement entropy using this formula. It's just 2 pi times the this integral. I can write it explicitly. X T00 rho. And this is something that I can calculate. So suddenly I can calculate entanglement entropies using this idea. And this idea is called the first law of entanglement, and it pops up in various places. Okay, and let me just finish there.